Hello everyone, I'm Yuhe Tang from Lab Research Group at the University of Pittsburgh. Today I'm going to talk about the experimental part of magnetically tunable 1D Coulomb drag experiment. Coulomb drag experiment involves two closely spaced but electrically isolated conductors driving currents through one conductor called drive conductor. A voltage will be induced in the other conductor called drag conductor if it's open, or a current will be induced if it's closed. From this phenomena, the scattering due to long-range interactions between charge carriers in different conductors can be understood. The scattering events, accompanied by momentum and energy transfer between two conductors, are helpful to provide additional insights into microscopic properties of interacting many-body systems. Therefore, Coulomb drag experiment is a powerful resource to study electronic relations. Previously, a lot of efforts have been devoted to 2D Coulomb drag, which basically involved two conducting layers. 1D Coulomb drag, which involves two approximately coupled nanowires, should be more interesting because electrons confined at one dimension are expected to have stronger electronic correlations. More exotic behaviors are predicted for 1D systems. For example, a 1D Coulomb drag was used to observe Wigner crystallization and Luttinger effects, and so on. A challenge for Coulomb drag experiment lies in the device fabrication because it's difficult to make two nanowires close apart while still prevent leakage between two nanowires. Before, most experiments were performed on Gaussian arsenide system with either lateral or vertical geometry, and nanowires are created by gating technique. Complex oxide is a system that's rich in physics. The system we are working on is lanthanum aluminate strontium titanate heterostructures. When a thin layer of lanthanum aluminate was grown on top of strontium titanate, a 2D electron liquid will form at the interface. The interface exhibits a lot of interesting properties, such as hysteretical reversible metal insulator transition, tunable spin optic coupling, tunable superconductivity, and electronically controlled ferromagnetism. All of these features are tunable, which gives us more control over the interface. In our lab, we developed a technique called conductive-AFM lithography, which allows us to create nanowires and study nanoscale phenomena at the interface. When 3 unit cells of lanthanum aluminate are grown on top of strontium titanate, the interface is insulating. However, applying a positive voltage to conductive-AFM tip as a top gate, one can locally induce the interface to undergo metal insulator transition and create nanowires. The width of nanowire can be as thin as 10 nanometers, and by properly controlled tip voltage, it can be further reduced to 2 nanometers. The process is reversible, therefore by applying a negative voltage, the interface can restore insulating state and the structure can be raised. This allows us to create nanostructures such as quantum dot, quantum point contacts, and superlattices. Nanowires are important for studying electronic correlations. By placing two quantum point contacts in the nanowire, in our lab we observe quantized transport, which confirm ballistic transport and the high quality of the nanowire created in our system. We are able to fabricate nanowire-based single electron transistor. Previously, by performing transport experiments on a single electron transistor, a new electronic phase has been discovered where electrons pair without forming superconductivity, and we also discovered tunable electron-electron correlations. Higher quality nanowire can facilitate Coulomb drag experiments. The geometry is straightforward. Our Coulomb drag device consists of two parallel nanowires, each conducted using a four-terminal geometry, which is suitable for both 1D Coulomb drag and other transport experiments. By properly controlled parameters such as tip voltage, we can create nanowires with lengths ranging from 100 nanometers to 10 micrometers, with approximately 10 nanometers interwire distance from 30 nanometers to 1.5 micrometers apart from each other. According to the measurement at 50 millikelvin, the interwire resistance is much larger than the typical wire resistance. Therefore, we can guarantee there's no, in this condition, there is no leakage current between two parallel nanowires. Two measurements were performed in Coulomb experiment. On the left is a configuration of voltage track measurement, sourcing current I1 in wire 1 with a DC voltage Vs1. We can measure the induced voltage V2 in wire 2, which is the drag wire, if drag wire is open, and we can measure 4-terminal voltage V1 in wire 1. The corresponding resistance is given by this equation. For example, in this configuration, R21 is the drag resistance and R11 is the 4-terminal resistance for wire 1. We can do the same when we source current in wire 2, and we can obtain drag resistance R12 and R22 for 4-terminal resistance of wire 2. Therefore, we can construct a matrix with diagonal terms being 4-terminal resistances for each wire, while off-diagonal terms being the drag resistances. On the right is the configuration for current drag measurement. By making drag wire 2 a closed circuit, we can measure the drag current I2 in the drag wire. The figure of merit for current drag measurement is drag conductance. Is conductance Gij defined by this equation. In this configuration, G21 is the drag conductance and G11 is the 2-terminal conductance for wire 1, which is the dry wire. Similarly, we can construct a matrix with diagonal terms being 2-terminal resistance for each wire, and off-diagonal terms being the drag conductances. We measure drag resistance in high magnetic field regime. Magnetic field is applied perpendicular to the interface and swept from minus 2.55 Tesla to minus 9 Tesla. At each magnetic field, a DC bias Vs1 across dry wire 1 is swept to change the current I1 in I1, and we can obtain drag resistance R21 as a function of drive current I1 and the magnetic field. First, we can see drag resistance is anti-symmetric with respect to the sourcing current. Extract the drag resistance along sourcing current plus and minus 17 nanoamps. We observe an oscillation of drag resistance with respect to magnetic field. We also took the current drag measurement. Magnetic field dependence of drag conductance G21 from current drag measurement was shown on the left. The figure on the right shows magnetic field dependence of drag resistance R21 measured from the same device with a voltage drag configuration. Drag conductance G21 is observed in both superconducting regime and high magnetic field regime, and is consistent with the drag resistance from multi-drag measurement. However, drag conductance G21 is noisier compared with the drag resistance. This may be because in the current drag measurement, the drag wire is a closed loop. Therefore, electrons move in the drag wire consistently undergo an energy dissipation during the motion in the drag wire for an open loop. As in the voltage drag measurement, electrons just need to move until steady state has been built where a voltage across drag wire prevents electrons from moving. Voltage drag measurements are also performed in superconducting regime. On the right are drag resistance R21 and the two terminal resistance of drag wire wire 2 as a function of temperature. From line cuts at 400 millikelvin and 600 millikelvin, we can see as temperature decreases, superconductivity shows up in the drag wire, and we can see an enhancement of drag resistance in the experiment. This may be because electrons in a superconducting wire can move without energy dissipation. Therefore, superconducting nanowire responds stronger to the interaction with dry wire. That's why we see an enhancement of drag resistance as drag wire enters superconducting regime. To sum up, we report 1D Coulomb drag experiment performed at non-thermal luminous strontium titanate interfaces in high magnetic field regime. An unusual symmetry of drag signal and non-zero bias and oscillation with respect to magnetic field are observed. We observe a large enhancement of drag signal in superconducting regime. We directly measure the drag current. Our Coulomb drag experiments can provide novel insights into electronic relations in low-dimension oxide systems. To know more about this data in high magnetic field regime, please stay tuned for the next theory talk. For other experiments in our lab, I recommend you to go to these sessions. Thanks for your time.